Welcome to EDU World Space.
For part A of the given problem, for the case where R is greater than R2, the field is like that of the point charge, so the potential V is given by K Coulomb constant times Q divided by R, where the potential was taken to be a 0, V is equal to 0 at R is equal to infinity. For part B, in the region R1 less than R and R is less than R2, we have electric field E is equal to Q divided by 4 pi epsilon times R3 minus R13, this divided by R squared, R2 cube minus R1 cube. If Vs is the electric potential at the outer surface of the shell, where R is equal to R2, then the potential at the distance R from the center is given by V is equal to Vs minus integral R2 to R e dr. This gives us Vs minus Q divided by 4 pi epsilon times 1 over R23 minus R13 integral from R2 to R of R minus R1 cube divided by R squared dr. So simplifying the expression gives us Q divided by, so this is minus sign here, not equal, divided by 4 pi epsilon 1 over R23 minus R13. Evaluating the integral, we get the expression that is R squared over 2, so R squared over 2 minus R2 squared over 2 plus R1 squared cube, this is cube here, so cube here divided by R minus R1 cube divided by R2. The potential at the outer surface is found by replacing, so we replace R by R2 in the expression found in part A. It is then given by Vs. Vs is equal to Q divided by 4 pi epsilon times R2. We make this substitution and collect the terms to find V. So V is equal to Q divided by 4 pi epsilon 1 over R2 cube minus R1 cube into 3R square 2 square divided by 2 minus R square divided by 2 minus R1 cube divided by R. Since density is equal to 3Q divided by 4 pi R2 cube minus R1 cube, this can be also written as a V of R, that is density of over 3 epsilon times 3R2 square divided by 2 minus R square divided by 2 minus R1 cube divided by R. For part C of the problem, for a case where R is less than R1, the electric field vanishes in the cavity, so the potential is everywhere the same inside and has the same value as at the point on the inside surface of the shell. We put R is equal to R1 in the result of part B. After collecting terms, the result is V is equal to Q divided by 4 pi epsilon times 3 over 2 R2 square minus R1 square divided by R2 square cube minus R1 cube. Or in terms of a charge density, we can write V is equal to rho divided by 2 epsilon times R2 square minus R1 square. For part D of the problem, using the expression for V of R found in part B, we write v function of r1 is equal to rho divided by 3 epsilon 3r2 square over 2 minus r1 square over 2 minus r1 cube over r1. This gives us rho divided by 2 epsilon times r2 square minus r1 square. Then v as a function of r2, we can write v as a function of r2 is rho divided by 3 epsilon 3r2 square divided by 2 minus r2 square divided by 2 minus r1 cube divided by r2. Further simplifying, we get this one 3q divided by 4 pi divided by 3 epsilon times r2. Further simplifying, we get v of r2 is q divided by 4 pi epsilon times r2. So the solutions agree at r is equal to r1 and at r is equal to r2.